Thanks, Robert. So I'm going to talk today about cosmology, which is the study of the universe as a whole. There are various other talks this week talking about detailed objects. This is where we're looking at the big picture and using all the things in that big picture to tell us more about it. We're going to start by talking about distances and talking about speeds. And to get some sort of idea of how far away things are, we're going to have to talk about how fast things go. So this is a fast human. He can run 23 miles per hour over about 100 meters, exactly 100 meters in about 10 seconds. But it's not very fast compared to a machine we can build. This is an airplane, it's a modern airliner, Boeing 787, and it can go 570 miles per hour. And that's 24 times faster. It can do this about half the distance around the world in about 15 hours. That's still not that fast compared to one of the fastest things we've built, maybe not the fastest, but certainly the farthest away thing we've built, Voyager. This goes 38,000 miles per hour, which is 67 times faster than that Boeing 787. It's so far gone about 12.2 billion miles, which is also 132 astronomical units. An astronomical unit is how far away the Earth is from the sun. And that's one of the units we use in astronomy more frequently than miles. It's also 36 light hours away, which means it takes 36 hours for light to get from us to Voyager, or for light to get from Voyager back to us. And since radio messages are also a form of light, that's how long it takes for us to talk to Voyager these days. And it's done that over 38 years. But that's still pretty slow compared to photons. Now, I haven't shown a picture of a photon here on this slide, but in fact, you can see lots of photons on this slide. They're coming from that projector over there, bouncing off the slide into your eyes. They go 670 billion miles per hour across 81 zetamiles. Now, a zetamile is kind of a unit I just made up. It's not completely made up because you can say a zettameter, and that makes sense. But no one really knows. It's hard to picture what a zetamile is. And this is how far they've been traveling since the beginning of the universe. That happens to be 13.8 billion light years, which, no coincidence, means the universe started about 13.8 billion years ago, if it took light 13.8 billion light years to get here. And so let's use some of these here to define units of how far away things are, so we can maybe try to wrap our heads around them a little bit better. So we'll start off with the light year. All right, this is how many years it would take light, including radio signals, for light to get from someplace far away to here, or from light to get from us to them. But normally we think about light from there to here because that's what we see. When we see a planet or a star or a galaxy far away, light is coming from there to here. We can also talk about Voyager years, which I'll briefly call VJers for short. Yeah, some of you know what that joke is. Don't be proud of it. This tells us how many years it would take for Voyager 1 to get there, if it was going in the right direction. So it's 16,000 or close to 17,000 Voyager years in one light year. Or, yes. However, a unit that astronomers use the most is a parsec, which, if you're a different kind of science fiction fan, you might think of as a unit of time, at least according to Han Solo. It's not a unit of time, it's a unit of distance. And we can put mega for 1,000 parsecs, or sorry, kilo for 1,000 parsecs, or mega for 1,000,000 parsecs. And this is what astronomers usually use. It's pretty close to a light year. It's only, it's about 3 light years. Well, what that means, the name of this is actually a great lead-in to how we actually measure distances in astronomy. So, what is a parsec? A parsec is an arcsecond of parallax, and I bet it's now perfectly clear what a parsec is. Well, okay, so what's an arcsecond? An arcsecond is a tiny, tiny angle. If you think about a degree, a circle has 360 degrees. An arcsecond is 1/3,600th of a degree, so it's really, really tiny. But it turns out this is about how blurry the images are for most big professional telescopes here on Earth. Maybe about half this, maybe about twice this for worse telescopes. And that's important because what parallax is just depth perception. So your eyes, you have 2 eyes, so when something's coming at you, say in a movie theater like this with 3D goggles on, you can tell that it's coming at you, even that's probably lying to you. But in real life, your eyes tell you how far away something is, because this eye is over here and this eye is over here. right? Now, as the Earth goes around the sun, it also moves. So if you look at a star while the Earth is on one side of the sun, say in the summer, and we look at what the star, where the star is when the Earth's on the other side of the sun, say in the winter, we'll see that the nearby stars move more than the distant stars. And this is a simulation of this, but it's magnified by 1,000 times. You can see the constellation Orion up here, and these are the actual stars in that patch of sky. And you can see how the near ones move and the distant ones move less, and your eye automatically figures out which ones are near and which ones are far away by how much they're moving. But this is very much exaggerated. The real stars don't move nearly this much. But our telescopes can tell that they're moving. They can tell that they're moving, about an arcsecond, maybe, or probably in some cases better than an arcsecond. Definitely, actually. And this is what a parsec is. If a star appears to move an arcsecond as the Earth goes around the sun, that means it's a parsec away. So how does this compare to things around us? This little circle is 1 kiloparsec. It's actually 1,000 parsecs. Now, this isn't a photograph of the galaxy. Can anyone guess why this is not a photograph of the galaxy? Feel free to shout it out. It's from the top, right? We don't have this view of the galaxy because we're stuck inside it. And so when we see the Milky Way, it looks sort of like, it looks flat because this is the disk and we're inside the disk. No one can take a picture from here, not even Voyager. And the reason is because Voyager hasn't gone nearly this far. In fact, this is 5.1 million Voyager years away, which means if Australopithecus had gotten his act together and stopped, hunting, gathering, and instead launched space probes, it would have gotten about this far today. Sadly, that didn't happen. So Voyager has gone a much smaller amount than this today. We can actually measure parallax out quite a bit further than this. There's a telescope in the sky right now, the European Space Agency's Gaia satellite, that will measure parallax extremely well, out to about this much of the galaxy. It'll do bright stars better a little bit, bright stars a little bit further away, faint stars closer, but this ballpark area. And this is 10 kiloparsecs, 10,000 parsecs, or 32,000 light years. It's starting to become not that useful to talk about Voyager years anymore, but I'll put it there just so we can stay consistent. So that raises the question, if this is how far away we can measure parsecs, how do we know what else is out there? How do we know what's going on beyond that? Well, to do that, we're going to zoom in on a star that's roughly here. This is the part of the sitting in the movie theater where you get to watch a movie. And then I'll explain what this star is. Zooming in, zooming in. And now the star is blinking. Now, lots of stars blink in different ways. And if you show up to the lecture tomorrow, I'm sure you'll hear quite a bit more about all the different kinds of blinking stars. This is a special kind that blinks in a certain way, and we can recognize stars like this from the way they blink. It also turns out that stars like this, which we call Cepheid Variables, are special because how bright they are depends on how fast they blink. So in the early 1900s, an astronomer named Henrietta Leavitt made this plot where she put a bunch of stars of brightness versus the days between pulses, days between the star blinking. And you can see, if you can tell how, we look at the star and see how fast it's blinking, we can from that read off how bright it should be. Now, because things that are farther away are fainter than things that are close to us, if we can tell how bright it should be, and we can tell how bright it looks to us, from that we can tell how far away it is from us. And we call this a standard candle. Now this is one of the most important discoveries in astronomy, and I'm not going to talk a whole lot about famous astronomers, but I'm going to talk very briefly about Henrietta Leavitt, because she got almost no credit for this. And she made this discovery at a time when women weren't even allowed to visit the telescopes. But she was one of the smartest astronomers of her day, and without this, a lot of stuff that other more famous people like Hubble discovered would not have happened.
Hey, Henrietta!
So using these Cepheid variable stars, we can map out where we are further out. So this is a bit of a zoom out. Here's our Milky Way galaxy. Over here is the nearest big galaxy to us, Andromeda. You can see that in the night sky with your own eyes if you're out in a dark enough place. And there's a bunch of smaller galaxies around each of us. Both of these galaxies are moving towards each other. And someday in the distant, distant future, don't ask me, I don't remember when, they are going to run into each other. This is 778 kiloparsecs, 700,000 parsecs. It's 2.5 million light years, and it's 39 billion Voyager years. Now, if you recall, the universe is only 13 billion years old, so it's really not useful to talk about Voyager years anymore, and I'm going to stop doing it. But just to reinforce, it's sort of bad news for those of us who are someday hoping for intergalactic civilizations. It's not going to happen. So zooming out a little further, that whole little group of galaxies is in here somewhere where you can barely see it. And out here are larger groups of galaxies, clusters of galaxies. This is called the Virgo cluster. And all these together are called the Virgo supercluster. And this is the area near us. We can still see Cepheids out this far. Now we can look at a group of, zooming out further, even more local superclusters. Here's Virgo. Here's another supercluster called Coma. And at this point, all of space starts to look pretty much the same in all directions. It's clumpy, but if you sort of blur your eyes, it looks the same everywhere. And if you zoomed out further, you'd see the same thing. In fact, the whole universe, we don't know how big it is, but it's at least 10 times as big as this. That's how far out we can see things like this. And it looks pretty much like this in all directions. This circle here is about how far we can see individual Cepheids. Now, this took quite a bit of work. We can't see very many Cepheids out here because they're really tiny, and they're usually in parts of really big galaxies. But the furthest away ones are about this far away. So we can measure distances using those Cepheid variable stars about this far. But it turns out that the reason we can't see farther than this isn't because things are too far away. It's because they also are far back in time. Remember, as I said in the beginning, light takes a time to move somewhere, so the light that we see now was actually emitted sometime in the past. So if we look at various faraway things, we can see what we're seeing isn't how it looks today, it's how it looked a long time ago in the past. So when we look at the nearest stars, I was finishing graduate school. Robert had barely met me. If we look at the center of our galaxy, it's about when the first humans arrived in North America. And it doesn't take much further for the numbers to start getting crazy. If we look at the Andromeda Galaxy, that's when there are saber-toothed cats making wonderful fossils for us to look at in museums. And the Virgo cluster and the Coma cluster, that's when the Himalayas started growing. That was a long time ago. And when the first reptiles evolved, even before the dinosaurs. Makes you feel kind of puny. So, what happens as we look further and further away? We look further and further back in time, or farther, I should say. Robert may never let me live that down. But we've also found that the farther away we look, the redder things are. Now that's weird. There's nothing that would obviously make you think further back in time or farther away that things would be a different color. To do that, I'm going to have to talk a little bit more about how light works. And I'll have to shout. So light is a wave, and we can think of it being something like this slinky. And the slinky is twirling through space. It's actually in light, it's electromagnetic waves. And what we think is making this light redder, and what we're pretty sure is making this light redder, is that space is actually expanding. Now, the color of light is determined by the distance between these little bits of waves, the different distance between the ups and downs in the waves. Now, if you think of those ups and downs as being the little rings in the slinky, as space expands, the distance between the little waves moves apart. And that changes the wavelength of the light. And since wavelength is what we see as color, things get redder. The way our eyes work, we have some cells in our eyes that are sensitive to red light, some blue light, some green light. And the ones that are sensitive to longer wavelengths are the ones sensitive to red light. So as the wavelengths increase, more of the photons get picked up by the sensors in our eyes that detect red light, and things look redder. And we call this redshift. So, if we put all that together, the redder something is, the smaller the universe was when the light was emitted. So the universe has grown since the light started moving. Now, if you think about this, if the universe is always smaller the farther back we look, we can guess that the universe is getting bigger. And that probably means the universe started with an explosion. It certainly seems like it started with an explosion, and that's what we call the Big Bang. This is not the Big Bang. This is a somewhat smaller bang. This is a firework here on Earth. But there's a few things we can talk about with this firework and how to relate it to the Big Bang. First off, the Big Bang doesn't work exactly like this. The firework has a center and it blows out from everywhere. And the Big Bang is more complicated than that. It's a very hard thing to wrap your brain around, and I'm not going to spend a lot of time on it, but I don't want you to get the impression that the Big Bang looks just like this. There is one thing you'll notice. All the little particles that are flying out of the firework are slowing down. They start out moving really fast and then they slow down. And the reason they slow down is because they're running into stuff. They're running into air. And the air pushes back against them and they don't move as fast until they stop moving, and then they sort of dissipate. And you can't see them anymore because they're not light. But they are slowing down because there's stuff in the way. Now in space, there's nothing slowing stuff down. There's nothing standing in the way. But we would still expect everything to slow down. And the reason we expect the stuff to slow down is because of gravity. Gravity, of course, pulls stuff in. It doesn't push stuff apart, at least not in our normal experience with gravity. The sun pulls on the Earth pulls on the moon, they all pull on each other, and there's no pushing involved. So we would expect that as the universe expands and is pushing all these galaxies further away from each other, that the gravity would start to pull them all back together. Now, if the universe started out exploding really fast, you might expect that gravity wouldn't be able to stop it, because the gravity also gets weaker as things get farther away. However, if the universe didn't expand fast enough, or there was a lot of stuff in it pulling it back in, the universe might expand a little bit and then stop expanding and then slow down and then collapse back together. But to see what it's doing, we have to find a new way of looking further. So this is a supernova remnant. A supernova actually, it looks just like a very bright star that lights up for about a month. But afterwards, it expands slowly, and if it's close enough to us, we can see a nice, pretty cloud of gas and dust like this one. This supernova went off in 1604, and it was observed by Kepler, among others. And this is what it looks like today. And when it was going on, it was the brightest thing in the night sky, and it was even visible during the day. But supernovae like this are very rare. We only see them in our galaxy maybe once every 100 or 200 years. But there are enough galaxies out there that we can actually see quite a few if we look in many other galaxies, many per year. But because they're so darn bright, and this is a very special kind of supernova, we can also use it as a standard candle. Just like the Cepheid Variable stars, how quickly this supernova brightens up and then fades away tells us how bright it really is. So, like before, if we can use how fast it gets fainter to tell us how bright it really is, and we can see how bright it seems to us, that lets us say how far away it is. Because stuff that's further away is fainter than stuff that's close. And that lets us see really far back into the universe, and it lets us make a plot like this. Now this is a complicated plot, so I'm going to spend some time explaining it. So each of these little dots here is a supernova that we've measured. And over here, this is how big the universe was when that supernova went off. And we can measure how big the universe was, not in an absolute sense, but how much smaller it was today or how much bigger it was than today. Using that redshift, we can tell how much the light got stretched out by how much it got redder. So over here is how big the universe is today. That's 1.0. This is when the universe was half as big as it is today. This is sometime in the future when the universe might be half again as big as it is today. Now down here, we have the time. And we can tell the time from how long it's taken the light to get us, because light always goes the same speed. And this is distance that we can measure from, we can measure the distance from how bright the supernova is. And from that, we can tell the time. So that, for each supernova, we can measure the redshift, which tells us this number, and we can measure the distance, which tells us this number. And we can make models of what the universe should do if the universe is is growing faster or growing slower, or crunching. And all these areas in this orange area, these are the universes that behave what we'd expect, right? They start out moving fast because it's exploding, and then gravity catches up, and it slows down, and maybe it collapses, maybe it just keeps expanding slower and slower forever as it gets tired, and gravity starts pulling on it. But as you can see, these supernovae aren't on any of these red lines that are behaving the way we'd expect. Instead, the supernovae show that the universe is doing something very, very weird. It's not just getting bigger and then slowing down the way we saw in that firework. It's getting bigger, it's getting bigger and speeding up. And why it's speeding up is a very big question. And it looks like the more empty space there is between galaxies, the more it speeds up. And the name we've come up for this effect is dark energy. So if you've heard of dark energy, this is all it means. Empty space pushes itself apart, and it makes the universe expand faster and faster. And we don't know what's making it go faster and faster. And since we don't know, we called it dark energy, because unlike particle physics, particle physicists who come up with great names for things, like quark, we just go with dark. So, this actually didn't sound too strange, at least at first, from the perspective of quantum mechanics. In quantum mechanics, there's actually a prediction for this, that empty space has energy, and that empty space would push stuff apart. So we can calculate from quantum mechanics how much that energy should push stuff apart, and we're going to run through something like that. The real calculation is much too complex even for me. I learned maybe about half of how to do this back when I was in graduate school, and that was a long time ago, and I certainly don't remember it anymore. But we're going to use an analogy. So the way you calculate this is something like summing up a bunch of numbers, each of those numbers getting smaller and smaller. So let's take this case, where we add up 1, plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, plus on and on forever. And this turns out is what we call a divergent series. If you keep adding it up, it just keeps getting bigger. If you imagine this line, it gets bigger, smaller, and smaller, but it keeps going up forever. So if you add all these numbers up, it goes to infinity. Turns out, if you Google divergent series, this is not what comes up. So here's our problem. This is just like the calculation in quantum physics. If you add up all the numbers, you get infinity. And that would be like saying the amount that empty space pushes itself apart is infinity. And that doesn't make any sense, because the empty space pushes itself apart that much, none of the stuff we see would ever form. No galaxies, no stars, no planets, no humans, no llamas, nothing. It would blow itself apart immediately. Yeah, not even any llamas. So the first thing we thought about, back before we knew about dark energy, was, well, maybe it's not infinity, maybe it's zero. And this isn't such a crazy idea, because there's a lot of stuff in the universe, and in physics in particular, where opposite things cancel each other out, like positive and negative charge. So people thought it wouldn't be such a crazy idea if there was something we didn't know about that exactly canceled each one of these. Maybe there's a -1 here, and a -2 here, and a -3, and a -4, and that cancels out the positive numbers, and if we add them all up, we get 0. Great. There's no dark energy, but we don't know about dark energy yet. And the world and the universe don't blow each other up, or blow itself up. And all the stuff we know about, humans, llamas, stars, galaxies, those can all form. But we know about dark energy, so we know the answer isn't 0 either. So instead we do a different trick. We say, well, let's not add up all the numbers up to infinity. Let's add up only all the numbers we understand. So we don't understand all of physics. We understand physics up to a certain point, and we think we know what's going on there. And we just say, well, let's pretend the stuff beyond this doesn't count at all. If we stop these numbers, we'd get 25 over 12. If you add up all the similar numbers in the quantum physics calculation, you get a number that's a little bit too big. It's actually a lot too big. So the real dark energy is 10 to the 120 smaller than what this quantum physics calculation predicts. Now, this is how we normally write it. If you were really trying to impress someone like I am here, you would write it out like this. This has been called the biggest or the worst prediction of physics, and I think that's probably accurate. I can't think of any other number in nature that is as big as this. This is bigger than Avogadro's number by quite a bit. This is bigger than the number of atoms in the universe by quite a bit. I can't think of any number that comes close to how big this number is. So that whole idea about quantum physics, quantum mechanics, and figuring out that calculation for how much empty space pushes itself apart, that didn't work out so well. There might still be a way to fix it, but to fix it, you've got to come up with something that can make a number go from basically this big down to almost 0. But there are other possibilities. It could be that gravity doesn't work the way we think. Our theory of gravity, which is also called general relativity, you may have heard of that, might be incorrect. And you can imagine ways, and this would also cause the universe to expand just a tiny bit. It turns out, though, that creating laws of gravity is really difficult business. There's a reason that only 2 people in history, named Newton and Einstein, have ever come up with a working theory of gravity. Now, it's quite possible there's some other theory of gravity out there. In fact, most physicists think there has to be another law of gravity out there because we don't know how to make this one work with quantum mechanics. But so far, no one's been able to come up with the law of gravity that even is self-consistent, let alone explains what the dark matter is, or what the dark energy seems to be doing. It's also possible it's a totally new force that we haven't seen anywhere else. There are a number of different forces in physics, some of them that are noticeable in our everyday lives, like electromagnetism, other ones that are not so noticeable, like what we call the weak force. And it's possible this is one we've never seen before. And this one, we actually came up with a good name for this, quintessence, which is fun to say. The problem with this idea is it's actually really easy to come up with new force theories. And they all basically behave the same way. So from all the data we have, we can't tell which, if any of these quintessence theories is accurate, because they all do the same thing. So that's a problem for theorists to figure out as well, and for us observers to go get more data. There's also some people who think that the energy of empty space, this dark energy, is basically randomly assigned to different parts of the universe. And our neighborhood of the universe, all of the universe that we can see, just happen to get a very small number. Now that's possible, but it's very hard to test this hypothesis. And so unless we can see that empty space maybe has a slightly different energy somewhere really far away, or we can come up with a better motivation for why it would just be random, this isn't a very satisfying answer either. And that's why physicists and astronomers are so interested in dark energy, because we think we understand how most of the universe works really well, but it has to have this one part, and we have no idea what's causing this one part. So, getting back to our mapping of the universe, let's look a little bit further away, actually quite a bit further back away, and more importantly, further back in time. This is what we call the cosmic microwave background. If we look far enough back in time, this is what we see. This is not light that our eyes could pick up. This is in the microwave range, which is almost to radio waves. And that's because the light that started out being light that we could see has been redshifted so much that we can't see it anymore. And this comes from back when the universe was so small and so dense and so hot that it was almost the surface of the sun. Well, it was like the surface of a somewhat cooler star than the sun, like a red dwarf. And back then, everything was hot and sloshing around, and you couldn't see through it, just like you can't see through the surface of the sun. But it turns out we have when stuff is just sloshing around and mostly the same everywhere, that's when physics models really work quite well. So we can make simulations of what all the mass was doing in the universe early, back when it was all sloshing around and super hot, and we can predict and we can compare those simulation predictions to what we actually see in this cosmic microwave background. This was measured by a recent satellite, again by the European Space Agency. There was another one by NASA, WMAP, which did a very good job of measuring this a bit earlier, and several other experiments on the ground. And from that really detailed data, that detailed map of what the universe used to look like a long time ago, we can compare that to our actually very accurate simulations of what the universe was doing. And we find another big surprise. Back when the universe was this small, there wasn't just one soup sloshing around. There were actually 2 soups sloshing around. And those soups would move through each other like they almost weren't even there. And we know that one of those soups was made up of pretty much all the stuff we see. The atoms made up of protons and neutrons and electrons. And the other soup doesn't seem to touch those things at all. It does seem to have gravity. We can tell that gravity was affecting how this soup is sloshing around. But we can also tell that pretty much nothing else was. In fact, the soup of the stuff that we don't understand is actually bigger than the soup of the stuff we do understand. So this is how much we think there is of stuff in the universe today. This big red part is dark energy. That's, if you add up all the empty space and you add up how much is it actually pushing stuff apart, it's this much of the universe's total energy. When you look at this green part, is that soup that we don't understand, what we call dark matter. And only 5% is the stuff we do understand, the protons and neutrons and electrons and even other weird exotic particles that are much more rare. So that's what dark matter is, the other big dark thing in cosmology. It just means that most of the mass in the universe is not made up of protons and neutrons and electrons. It happens to be invisible, but there's a lot of ways you can make pretty much invisible stuff out of protons and neutrons and electrons. This is much more special than that. It's made up of something we haven't seen yet in terms of what particle it's made of. But there's other evidence as well. In fact, this evidence came first for dark matter. So this are some simulations of galaxies. They're not real pictures of galaxies, and you'll see that in a moment as I make this move. So stars rotate around galaxies, and if there wasn't any dark matter, the stars would move slowly around the galaxies because there wasn't much in the middle pulling it in. Over here we can see what really happens. The stars have to move quickly because there's a lot of stuff pulling them in. And if we started with this one and the stars were moving that quickly and there wasn't dark matter in the middle pulling it in, the stars would just fly off. Like a person on a merry-go-round that's going too fast. And while we can't see stars move this fast in real galaxies, we can see how they move if we look at them edge on. We can see the stars moving towards us and the stars moving away from us. And we can see how fast they're going, and we can see how much stuff there has to be in the middle to hold them together. And we can tell from how many stars there are in the middle and how much gas there is in the middle that there's not enough to hold all those stars in if they're moving that fast. And that's another piece of evidence for dark matter, that there has to be more stuff that we can't see that is holding all of these stars in that are just zipping around the outsides of galaxies. Another piece of evidence is called gravitational lensing. And this is a bit more of what I work on myself. So if we start with something bright out here, this is just a cartoon, it emits light in all directions. Right? This is a star or a galaxy or a quasar. And over here we have something made of mass. Maybe it's got lots of dark matter, maybe it's got lots of regular matter too. The light rays get bent by that matter. So some of the ones that were going up here end up down here, and the ones going down here also end up here. And you can imagine this going in all directions. So some of them go out here and back in, some go that way and then back in. And then when we see them over here, it looks like these light rays actually came from stuff back here. So it looks like there are two things, not one. It's a mirror image, but a mirror image around a circle almost. And in fact, if you want to see this effect, and you have a wine glass, it's too bad I don't have a wine glass here, I should remember to bring one, and you look through the stem of the wine glass, that actually gives you good, and you can see the light kind of making circles in the wine glass. That's what gravitational lensing looks a lot like. It turns out that's because how dense the wine glass is as you look down the stem is similar to how dense galaxies are as you look at them face on. So here's what that looks like in an astronomical image. So this is a bright cluster of galaxies. All these yellow things are galaxies that are in the foreground. They're associated with a whole lot of dark matter in here. But you can also see little faint galaxies, little streaks around the outside. And each of these are lined up with another one on the other side. So there's something in the background that has a light ray going out that way and one going out this way. And they get combined back in, so when we see them, it looks like they're coming from two places. And we can use this to measure how much dark matter there is here, because how much the light bends depends on how much matter there is, both the light matter and the dark matter. And we can measure, and in fact map out the dark matter that way. So, this is what we know about the universe right now. What are we doing to learn more about it? Well, of course, that's what brings us all here today. We all work with this project called the Large Synoptic Survey Telescope. Another example of why astronomers shouldn't get to name things. Because this describes what it does, but it's not, it's not quark or quintessence. Best names tend to start with Q's. So it's why we're here in Bremerton. It observes half the sky every couple of days, maybe every 3 days, depending on how we operate it in the end. It lets us find a lot of new things, moving things, changing things. That includes finding more of those supernovae that we use to map how the universe was expanding as a function of how old it is. It also lets us find stars that have parallax. It's not maybe going to be as good as other things at finding parallax, but it will find a lot of them. And it lets us find those Cepheid stars that blink. So something like this lets us find a lot of those objects that tell us how far away things are. But we can also add the images together in various different ways to get a better picture of the things that don't change, or don't change very much. And that's all the galaxies, essentially. Galaxies are all far enough away that they really don't change much when we look at them. And they're big enough, I guess, more importantly, that they don't change when we look at them. And this is what I work on. And the way we use this is we map the dark matter, and that lets us measure the dark energy. And that's because we have simulations of what dark matter does. So we can start a simulation that just has dark matter all over the place in the same way that it would be roughly from that image of the cosmic microwave background, back as far back as we can look. And then we can just let gravity take its course and pull stuff together and form structures like galaxies and clusters of galaxies and stars and planets. Now this is a simulation that's of about the size of our Milky Way. As we watch it, you'll see it form into more of a recognizable kind of clump. But you can see it's all this nice stringy, filamentary, spiderweb kind of structure. And the details of how dark matter works and how dark energy is pulling everything apart at the same time all go into the simulations. So you can make a simulation for one value of dark energy and one way dark energy changes with time, and another simulation with a different prediction for how dark energy changes with time. And we can use these simulations to tell us about what we think dark matter and dark energy should look like in the real universe for different kinds of dark matter, different kinds of dark energy. Just let you watch this nice picture of a galaxy coming together. You can see up at the top how long it's taken. A giga year is 1 billion years. So it's going pretty fast. Since this is a galaxy-size simulation, each of these little clumps of things are maybe a baby galaxy, a dwarf galaxy orbiting it, maybe a cluster of stars. So even within our own galaxy, there's a lot of little clumpiness. Wow, this is a long movie. We get to take a break. I'm going to take a drink. And we can definitely see some clear dwarf galaxies forming up here, in addition to the big one in the middle. Now, as I said, this is just a simulation of one galaxy, something like our own Milky Way, in order to help us better understand the detailed structure around our own Milky Way, which I think is something that you may have heard about in the talk on Monday. We can also make similar simulations of much bigger areas, of areas that are as big as the amount of the universe we can see. But when we make simulations that big, we don't get the same level of detail into what's going on in an individual galaxy. But with lots of different simulations with different sizes, we can get a pretty good picture of everything. Question?
Different colors mean anything?
Yeah, the overall brightness says how dense the dark matter is, and the colors tell you actually how fast it's moving on average. So it's not actually the colors you'd see if you were looking at this through a telescope. Good question. All right, so here is what some data looks like of the same thing. Here's a simulation where we tried to put some galaxies on top of that dark matter. That's difficult because it's actually much easier to simulate dark matter than it is to simulate the normal matter on top of the dark matter. And here's a map of galaxies from the Sloan Digital Sky Survey, where Robert did quite a bit of the work. And you can see that it makes the same kind of structure, sort of spider web, stringy kinds of things. And we can tell we can measure how clumpy these structures are and how clumpy these structures are, and that tells us whether this model, this prediction for what the universe would be like, and the parameters and the details of how dark energy works, whether those numbers were correct. But this is tricky with galaxies, both because it's difficult to simulate the galaxies, and because the galaxies don't tell you exactly where the dark matter is, and most of the stuff is actually dark matter. So another way you can map out this is using gravitational lensing, as I said before. So if we zoom in on one little piece of this image, we can see that not only are there multiple images, but there are also images that get curved. The center of the cluster is way up here in the corner, and all of the background things are curved in sort of a circle around it. Galaxies that may have been facing this way are now stretched out to face this way, and that's one of the things that gravitational lensing does. It stretches things out around where the mass is. And it turns out this happens even when the mass is small enough, or the mass is far enough away from the background light that you don't even get multiple images anymore. You just get one image, but it's kind of stretched out a little bit. And because this happens everywhere on the sky, there's always something in the front and always something in back, you can always see a little bit of stretching around where the matter is, around where there's more matter, and a little less stretching where there's less matter. And we can use this to map where the dark matter is on the sky. But it turns out that's pretty hard. So here's some cartoon galaxies. These are all just little green dots, but they're roughly the right sort of shapes for galaxies. Right? And they're all randomly oriented. And if we add some lensing, if we imagine there's something massive right here in the middle, that's how much they change. Let me run that by you again. And this is actually for a pretty darn massive thing in the middle. Most of the time, it's not. It's about 10 times smaller than this effect. But it gets worse. Back when I told you about how gravitational lensing worked, I lied a little bit. So the light goes out in all directions. Something's in the way. The light gets bent around it. It doesn't hit us next. It hits the atmosphere. And then the astronomer on the other side of the atmosphere is sad. Because the atmosphere blurs things out. And your telescope does too. And in fact, it blurs it out quite a bit more than the lensing stretches it. So here's those same cartoons. Here's how much things typically get blurred out by the atmosphere. So everything gets blurred out, it gets a little bit smeared, it gets a little bit bigger. Now if we take those smeared galaxies and we add lensing on top of it, that's how much it changes. So in order to figure out what the difference is between this and this, we need to know what this is doing first. We need to understand how the atmosphere and the telescope smear all of our galaxies in the very tight, excruciating detail. And the way we do that looks something like this. So we start out with a real galaxy over here. It's small, it's tiny, it looks far away. It gets stretched out a little bit by gravitational lensing, and then it goes through the atmosphere of the telescope and it gets blurred out. And then we have to detect it on a digital camera, and there's a bunch of noise, and it's even harder to see. So we need to go from this to figuring out how much this thing affected that. Now there's one more thing that helps us here though. Stars are really tiny. Stars are so small that except for the very nearest stars, they're basically just points. We can never tell what their width is. But they're also smeared by the atmosphere in the same way. And we call this, because it smears the point, it spreads the point out, we call this the point spread function. And the stars also get noise in kind of a similar way. So if we look at how the atmosphere and the telescope and the camera are affecting a star, that also tells us how they affect a galaxy. So we can use the stars to come up with this point spread function. We can make a model of the galaxy. We can say, well, maybe it's an ellipse that looks kind of like this. We can smear it by our point spread function, and then we can compare that to the data we have. And we can do that for a lot of different model galaxies. We can try galaxies with different sizes, different orientations, different centers, and we can find one that looks the most like this galaxy that's noisy. Problem is there's a lot of galaxies. So this is an outline of what the LSST camera looks like. This right here is a moon to show you how much of the sky it sees. So it sees a fair amount of the sky, but not a huge amount at once. Each of these is a CCD, a single detector, and about half of one of these little boxes is the size of the detector in your iPhone. So this is a 16 megapixel CCD right there. And it's actually a much higher quality CCD than the one in probably any professional camera. But one of these little CCDs has this many galaxies on it. So on the whole thing, there's a whole lot of galaxies. And then you think, this is only a small bit of the sky. We're going to see half the sky in this much detail. But we're not just going to see it once. Here's what the camera looks like again. And we'll look at the sky here. We'll look there, 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 there. And then someday, maybe 3 days later, we'll come back and we'll do this. And we'll come back 3 days later and we'll do this. And after 10 years, we'll have 1,000 images over every patch of the sky. So, what we're trying to do is we're trying about 200 different galaxies, different sizes, different shapes, different positions, for each of 18 billion galaxies and stars, in each of the 100 images in which they appear. And that's only in year 1. In year 10, it's 37 billion galaxies and 1,000 images. And with all of this, we can tell exactly how much all those tiny galaxies have been stretched, and we can map the dark matter in between, and we compare that dark matter to the simulations that tell us about dark energy. So, to sum it all up, what have we learned? Space is big. It's really big. It's bad news if you want to go to another galaxy. It's bad news probably if you want to go to another star. But don't give up on going to another star. Space is growing, and it's weirdly growing faster and faster. And we physicists have no idea why it's growing faster and faster. We actually understand pretty well in detail that it is growing faster and faster, and we can measure pretty well how much it's growing faster and faster, and we'll do that much better with LSST. But we don't have any idea why it's growing faster and faster. And that means it's really important for us to measure out the details of how it's growing. Is it the same everywhere? Is it the same in every direction you look? Is it changing from the beginning of the universe to now? And finding out those things will let us learn more about what theories of dark energy could be correct. And we can map it almost all the way back to the beginning. We can map it all the way back until it's too hot and too dense to even see through it, like it's the sun. But we can't see all of it. So we don't know how big the universe is. Not because we can see the edge of the universe, but because if we look far enough away, we're looking back to the beginning of the universe. And so the universe might be the same. It's probably the same, much further out. Maybe it goes on forever. We don't know. But we can only see as far back as time will let us see. But by mapping all the stuff we understand, and the stuff we don't, this dark matter, and comparing it to simulations of the same, we can test the series of what the dark stuff, both the dark matter and the dark energy, are. And LSST will help with this quite a bit. It will provide a huge amount of data, and it will give us a really great way to map out the dark matter all over the sky, to find more supernova, to map out the galaxies and see what the dark matter is doing with the galaxies. But it's a huge task to analyze all that data. There's a ton of pixels, and we have to do something with all of those pixels. And I think that's about it. Thank you all very much, and I'm happy to take any questions. All right, first question up here.
How far away is Earth away from the black hole?
Earth away from the black hole. Actually, we can see that here. There might be some Earth on the beginning. Nope. There we go. So, Earth is about here, and the nearest black hole I think that or the nearest big black hole we know about is in the center of our galaxy right there. So it's about 10 kiloparsecs, about 32,000 light years. There might be other black holes that are closer, but this is the big one.
Is dark matter both attractive and repulsive?
Dark matter?
Yeah.
Dark matter seems to be only attractive. It seems to just do what gravity does to everything else. as far as we know, it's only dark energy that's repulsive, and it doesn't seem like there's a relationship between the two. There are some people who have theories that try to combine them together, but they generally don't work quite as well as the theories that keep them separate.
Reading in National Geographic, can a black hole we think of as, is it light in that mass that it's actually drawing light of sucking it in and it can't escape?
There is a point at which if light goes too close to a dark hole, to a black hole, it can't escape. But the effect of a black hole is so strong even further away from that, that on the whole, black holes are actually generally very bright, because we see the hot gas that's around them that isn't close enough to get sucked into the black hole.
Okay.
Doctor, the picture of the cosmic microwave background was fairly clumpy.
Yep.
Now, can we or do we correlate that clumpiness with the way we look at the current structure of the universe, particularly with all the superclusters and the great Sloan Wall as an example?
We absolutely do, and that's actually a very hot topic in cosmology today. One thing you may have noticed about that, I'm not going to go all the way back to the picture of the cosmic microwave background, but that was a zoomed out picture of the whole sky, which means for a long time, up until very recently, we could only see the cosmic microwave background in a very coarse scale. We couldn't see the details that are the size of, say, galaxies. And only recently have we had surveys of the cosmic microwave background that lets us see things that are as small as the galaxies and the galaxy clusters that we see in the optical with telescopes like LSST. So now that we can do that, it's a very useful thing to try to compare the cosmic microwave background to the foreground galaxies and clusters. How big are black holes? So black holes come in all kinds of different sizes. It depends on how much stuff they've already sucked in. The more stuff a black hole has sucked in, the larger the area it affects. And so the black hole in the middle of our galaxy is very big and affects a lot of stars right around it. And there seems to be ways that it can affect even the whole galaxy, but it's the further away you go, the less it affects you. Another question?
If something gets sucked into the black hole, does it explode?
The stuff that actually gets sucked all the way in doesn't explode. But usually when stuff gets sucked into a black hole, some of it flies off and some of it gets sucked in. And so as all of the stuff gets sucked in together, all the stuff that doesn't quite get sucked in instead looks like it's exploding. Question back there?
So it's in this picture, the Milky Way is in real life is it actually?
What colors is it? So it's many more colors than you can even show on this picture. I think I don't know if pink and blue are the prominent ones, but there are certainly blue stars and red stars, and we see quite a bit of both of them and things in between.
Yellow at the center.
Yellow at the center. Yes, that's also true. Out here in the edges of the galaxy, what we call the spiral arms of the disk, you see more bluish stars because bluish stars are younger, and there's more stars being born out in the bluish parts of the disk. As you get in closer, you get to see more old stars, and old stars tend to be more red. That's because red stars last a long time, and blue stars tend to die somewhat faster. So if all your blue stars have died, all you have left are the reddish, yellowish ones, and that's why it's yellower in the center. Question there?
Can you talk a little bit about the data processing pipeline?
I can talk way too long about the data processing pipeline. The challenge here will be talking just a little bit. So we first look at every image individually as it comes off the telescope, and we try to match up exactly where it is relative to all the other images we've taken of the same part of the sky. And we try to figure out what that point spread function is. And those are some of the most important things we do early. After that, we add up all the images together to try to find all the things at the very faintest. You can only see them when you add them all up together. And once we've found all the things by adding the images together, then we go back to all of the individual galaxies and all the individual stars and model them individually. Because that's better in some respects than trying to add them together and modeling what you get when you add them together. It's all very much computerized. This will take quite a big supercomputer.
Or a lot of Henrietta Leavitt.
Yeah, this is not something where if you have, you'd have to have way too many Henrietta Leavitt to solve this problem. Question in the far back? All done? All right. All right. Appearance.
What happens if you get completely sucked into the black hole?
We actually don't know. The question is, what happens if you get completely sucked into a black hole? Now, once you're inside the black hole, nobody knows what happens. The laws of physics are actually kind of contradictory about what happens. What we know for certain is you wouldn't survive getting into the black hole in the first place, because the gravity would rip you all apart, and there'd be all kinds of hot gases, and it'd be as hot as the sun in a lot of ways. So you wouldn't get close enough to the black hole to find out. Not something you want to try.
Wasn't it Hawkins that said if you didn't die, it would look like you were dying. You were being exploded and brought apart at the event horizon.
I think the problem with looking at what happens when you get into a black hole is that there are many different perspectives, and some of the perspectives see entirely different contradictory things. From one perspective, it seems like you're just falling into the black hole forever and you never actually get there.
Right.
And other ones it may seem like nothing even happened.
Like the gravimetric time dilation.
Yeah, exactly.
So, okay.
You had a question, Mike?
So you said it's a tinture process from the day y'all start. Is there an estimation to how long the data processing could take?
We've planned the amount of computing power we have in order to be able to reprocess all the data we'll have taken every year. So every year we'll have a new data release that has all the data we've taken up to that point.
But like whenever you said you're gonna stack everything at the very end, is that just like all the data you just basically?
All the data in one patch of sky is just added up. After we aligned it so that it matches up exactly and so on.
And that data is going to be open source, right?
Yeah, the data will be available. Now, if you wanted to download all of it, you'd probably need to wait in line a long time. But you can look at any small part of it very quickly.
My question is, reading a little bit about LSST historically, it said it was originally designed as a dark matter, dark energy search.
Yes.
Is that one of its primary?
That's one of its primary things. There are three big things that the LSST is set out to do. It will do other things well, but the three big things are dark matter, dark energy, mapping the Milky Way, and exploring all the things that change in the night sky.
And meteors.
Yes, one of the things that...
Because Congress mandated it, all those scientists, right?
If you're taking images on a schedule and you have some break or something where you stop, do you resume where you stopped, or do you resume back into the schedule?
The details of what you look at next is actually, that's also a very complicated computer program. Because where you want to look next depends not just on all the things you've observed, it depends on where the moon is, where the clouds are, what happened last night, whether there was rain, and there's a very complicated computer program that will decide where to go next. It's very unlikely that if you have a break, you'll go exactly to where you were before. But it's one of the possibilities that program will look into.
Does dark matter propagate gravity waves?
Yes, dark matter seems to behave along with respect to gravity the same way that regular matter does. And so if you wiggle dark matter around, it will create a gravity wave, just the same as you create a gravity wave if you wiggle regular matter. Over.
Two-part question. Is all dark matter connected to each other? And if it's not, is dark matter as different as I am from Usain Bolt?
Dark matter seems to be much more similar. It's more like a continuous cloud that's maybe clumpier in places, but we don't know what it's made of. Most people tend to think that it's probably just one kind of particle that's zipping around and forming clouds, like air or water, but less dense. But there's possibly that there's multiple kinds of dark matter. It's very unlikely that it's as complex as humans are, because humans and all the stuff we see on Earth gained a lot of complexity because we interact in lots of different ways. If one person runs into another, they stop, and that's not how dark matter works. It tends to go through itself. And that makes it very hard to form very interesting clumps. Question?
Yes. In relevance to time, the older universes do gain or lose dark matter?
It looks right now like the amount of dark energy stays pretty much the same. Dark matter, sorry, stays pretty much the same.
Regarding the Cepheid variable and measurement of distance, what's the limit there in light years?
Ooh.
Is it within the Milky Way, or?
It's outside the Milky Way. The Cepheid variables we can see out to there. So we can see the nearest superclusters. If we use the Hubble Space Telescope and point at it for a long time, we can see really far away. It's very hard to see Cepheids this far. It's much easier to see Cepheids sort of this far away. But the farthest ones we've seen are this far away. 13 billion light, or a billion light years.
Another question is, if we're looking at this and in the context that we're looking at dark matter and that, but like the nebulas and the ones that are spitting out stars that we've seen, I've seen them in National Geographic and stuff on TV. But now is that dark matter that might have over the past billions of years has been compressed into what we know as nebula and start spitting out stars?
The nebula we see are made of regular matter. It's gas clouds, other kinds of atoms, but the stuff we see on Earth may be in slightly different forms. And there might be slightly more dark matter in some of those clouds, but not very much more. And the stars and the nebulas themselves are regular matter.
The schedule you guys talked about for the last couple of days has been 10 years. What happens after the 10 years?
Lots of people have various ideas on what to do there. I think we probably won't know until we know what technology is going to be available then. You can imagine all kinds of new kinds of cameras you could put on this that don't even exist today. And I think a lot of people are hoping it'll be one of those things.
About how much would you say, do you think dark matter creates more gravity than dark matter?
Well, pound for pound, it's exactly the same. But the dark matter, there is more dark matter. So it creates more gravity in just exactly the proportion that there is more of it, which is about a factor of, that's 6, I think. It's about 6 times as much dark matter as regular matter. Oh.
One would think there'd be an average or a correlation between the size of a galaxy or a galaxy cluster and the amount of dark matter. Are we finding clouds of dark matter that are lacking regular baryonic matter?
That's a very hot topic as well. We certainly find galaxies that have much more dark matter in a very small amount of stars, especially for small galaxies. We haven't worked out the details of what makes something have more dark matter versus less. We don't think there's likely to be much out there that has only dark matter and no stars, or only stars and no dark matter, except in maybe very small scales. But it's an interesting thing to look for. Lots of questions. Let's go to the back there.
Sure thing. How about, that's great, just to follow up on that question, how about over the course of time? So as we look back, does dark matter seem more or less dense in the past?
So what tends to happen is that the dark matter stays a little bit more spread out than the regular matter, but they're related to each other. So for instance, in our own galaxy, the dark matter goes out quite a long distance, but the regular matter is mostly closer in. But it all goes out, everything goes out a far ways. And that's because, as I said before, the dark matter doesn't clump, it doesn't stop when it runs into itself. And so it doesn't clump as well as the regular matter does.
So dark matter, it doesn't react the same way with regular matter. Either it passes right through it. So is it related to that, I forget that other research where they have the big underground sensor with water.
You're talking about
trying to detect particles going
Right, so the question here is about other physics experiments that try to detect particles going through the Earth. And those are probably neutrinos. And dark matter is actually thought to behave a lot like neutrinos, where it goes through almost everything, and it's very hard to stop it. But it is possible to maybe stop it. The difference is we know that dark matter particles have to individually weigh a lot more than neutrinos. There aren't enough neutrinos to explain what we see as dark matter. But you can think of dark matter particles as, in a lot of ways, just very heavy neutrinos. At least that's what we see. It's going through us right now. Maybe not very many, but they are.
Is the construction of the telescope, is that taking into consideration possible retrofits or repurposing after the 10-year and all that, or is it just being exclusively built for this purpose with nothing in mind?
It's being built with regular maintenance in mind, and the idea, I think, that someone will do something with it in 10 years, but that's not what the money is to do. So the funding for what happens after 10 years, it has to come from some other proposal, but we're certainly not being planned to collapse at that point.
Dark matter being created or destroyed?
Dark matter be created or destroyed. It can technically, but it's difficult, and it's likely to not happen very much. So one of the ways that dark matter can interact is it's very unlikely, but if two dark matter particles hit each other, they can disappear, or we think they might be able to disappear and turn into a very energetic ray of light. And we look for those rays of light. But that happens very rarely. And it's not enough to affect how much dark matter there is overall in really any way that matters.
Since dark matter doesn't really have contact with itself, is it possible to fit more amount of dark matter in volume than with normal matter?
It should be possible to fit more. The problem is it's actually getting it into the container and holding it in the container. Question there?
My understanding, you're taking these photos constantly, all the time. But that supposedly help you identify the pattern of dark matter and dark energy? That's the purpose of that?
The reason we're taking many pictures rather than just one is more for finding the things that are changing. The dark matter changes slowly enough that it wouldn't matter much if we could take one really long image versus taking lots of short ones. But because taking lots of short ones works just as well as taking one long one, and taking many short ones helps other scientific goals, we don't mind that they take many short ones. Did that answer the question?
That's supposed to help you identify the characteristics of dark energy and matter, that there's some type of pattern that affects the planets or galaxies?
Not very much, because the dark matter, the patterns in the dark matter are patterns on the sky, and they don't change very much in time. So it's going to be the same pattern on the sky no matter when you look at it. But it's a very faint pattern, so we have to look at it for a long time. Does that make sense?
So do we know the shape of the dark matter around the Milky Way, disk or oval?
We know roughly, and maybe not so much about the Milky Way, but about other galaxies that look like the Milky Way. And in general, it seems like, well, many galaxies are disks that are flat. The dark matter, even for those disk galaxies, is not a disk. It's sort of a cloud. Question for that?
Why in the southern hemisphere and not the north?
Yeah, so why in the southern hemisphere versus the north?
I mean, like, why is it being held in
There are basically two sites on Earth that are the best places to build telescopes. There are many other almost as good places, but the two best places to build telescopes are the summit of Mauna Kea in Hawaii and on mountaintops in Chile, because they're very high and they're very dry and there's not much between the telescope and space. And that goes down to details of how the weather works and so on. Now, there's a lot of telescopes already on Mauna Kea, and it's expensive to build telescopes there, and there's some opposition to building new telescopes on Mauna Kea. And since the mountaintops in Chile are a bit more welcoming to new telescopes, and it's just as good of a site, that's why we chose to build it in Chile.
Like, how do you go about like getting a permit to build a telescope?
There's certainly quite a bit of negotiation in all those, and that's not my area of expertise. I think generally the government of Chile is very supportive of building new telescopes, but there's a lot of negotiation that goes on about who's paying for what, who's working for what, who has rights to look at the data, and all kinds of details along those lines.
But the president of Chile came to the groundbreaking ceremony. They're very positive about this experiment.
Question back here?
Yeah, about dark energy, I was scribbling rapidly about trying to fix this. Dark energy ties in with quantum mechanics or quantum theory, but it does not tie into general relativity and gravity wells.
It could do either one. We actually don't know which one of those things, if either of them, explains dark energy. They're just possibilities for what it could be.
Okay, so we're on the edges of tying all this together.
Yep.
In an area where there is dark matter, do they know much about the internal motion of the dark matter within that area? Like a wind.
Well, I think most of what we know about that, the question is, do we know about how the dark matter moves and whether there's winds of dark matter in areas? And we don't have much observational evidence for how it moves. But we do have very detailed predictions from our simulations about how it moves. So we have very good guesses based on how clumpy the dark matter is and so on about how it's moving. But we have a very difficult time measuring how it's moving. Question? Is the LSST open to everyone? All the data is definitely open to everyone. And there are going to be various facilities that I'm sure that you'll be able to go on tours. I'm not sure if you'll be able to go on a tour of the actual telescope, except maybe on special occasions when we're celebrating or something. It's hard to get to as well. I think even most of the people working on the LSST, there aren't going to be that many of us who actually go to visit it.
Jim, may I recommend we take one more question, and then anybody wants to leave if they have more questions, Jim, you can come on down. But we have one more question.
All right, let's have one more question from someone who hasn't asked one already. All right.
Do you plan to visit it yourself?
I don't know. I would like to at some point, but I also have to admit that my own job probably doesn't require me to visit it. All right, thank you all, and feel free to come back.